So welcome to today's webinar. My name is Matthew McKnight. I'm a technical specialist working out of the Melbourne office. And today we're going to be talking to you about predicting weld sizes using Autodesk Nastran In-CAD. So just a quick agenda for the session. Start out talking to you a little bit about weld terminology, some of the challenges in predicting weld stress or stresses in welds, common techniques for modelling welds in FEA. We'll then move on to working through some examples of static weld sizing and look at some of the issues around common configurations and loads and complex geometries and loads, and then we'll wrap it up with a quick summary. Prior to getting stuck into the content of the webinar, I do want to extend a thank you, a bit of an acknowledgement to Vince Adams, and I'm going to be doing more of this in coming webinars. A lot of the content that we present here is often contributed to or created by other parties. In this case, that is the case, and Vince from the Autodesk team, he's the global product specialist in our simulation group, has spent a lot of his career learning all about the things that we're about to talk about today, but also in preparing this presentation, a lot of time documenting them. Vince is very well known inside the industry. If you've been in finite element analysis for any more than a couple of years, you've probably heard his name before. And this is actually a subset or a smaller version than the YouTube video that's available called Predicting and Validating Welds with FEA in Autodesk Nastran In-CAD. So if you're after a more comprehensive webinar, you will find further information there. So let's just talk a little bit about the Autodesk simulation portfolio, because a lot of people still know Autodesk as the AutoCAD company. And then those of us know that beyond AutoCAD predominantly think about Inventor. They're not aware of the investment that Autodesk has made in terms of simulation capabilities. And you can see a snapshot of some of those capabilities here. We've got the structural mechanics capabilities, some of which we'll be talking about today. But we've also got a range of other simulation portfolios that can support the design of your products in a range of types of, whether it be products or industries, such as structural architecture, thermal flow, such as CFD, molding processes with industry-leading tools such as mold flow, and then even composites analysis in the form of Helios. If we look at just the mechanical simulation portfolio, there's really two predominant tools that we refer to. Sim Mechanical, which is a standalone industry standard solver, but then we also have a CAD embedded, we have our Nastran portfolio of tools, and Nastran comes in essentially two flavors. An embedded tool, and CAD embedded tool, not only available for Inventor but also available for SolidWorks users as well. And then a standalone solver. The Nastran solver comes as a standalone product as well, in which case you would use it with your own pre and post processor. In essence, using the In-CAD version, you're effectively using the same solving capabilities that have been given access to you by using Inventor or SolidWorks to do your pre and post processing. So let's get into the content of today's webinar. Firstly, what do we need to know before we get started? Well, I need to stress that it's very unlikely that you will find that FEA stresses on welds will match that which are measured on an actual weld. What do we mean by this? If you were to run an analysis, come up with some results to show you stresses on your welds, if you were to then go and measure them, it's unlikely that you will find correlation or the exact number that you're looking for. So stresses are definitely an approximation inside of your FEA packages when you're looking at the welds themselves. Secondly, just because you have better CAD doesn't necessarily mean you're going to get a better result. So what do we mean by this? Is that just because you're going to try and reflect the weld bead in more detail doesn't necessarily mean you're going to get more accurate results. And the value of FEA on welds is to help you size them outside of FEA. So it's not about actually getting your FEA tool to size the weld for you. It's about what information can I gather from my analysis results that I can then use as a means for sizing the welds. So there are a number of reasons for all of this, and I'll cover some of them in more detail today, but please keep these factors in mind when you're trying to understand welds on your welded structures. Let's have a quick look at some of the weld terminology. And hopefully many of you have seen similar illustrations like those that are shown here, but let's quickly talk through some of the critical aspects relating to our conversation today. Firstly, we have the theoretical throat of the weld, and this is the distance through the middle of the weld. You can see it on our screen on the left-hand side, highlighted in red there to show the size of the weld, and on the right weld, you can see it on the bottom right shown as well to show you that theoretical throat dimension. We also have the actual throat, and this is often unpredictable because it largely depends on the weld. And you can see the actual throat is the measurement from the root of the weld up to the top face of the weld. The leg of the weld is the distance down the side of the weld, so you can see it here on the right-hand weld down the left-hand face, and you also have the same across the bottom face. And the light grey area surrounding the outside of the weld, that's likely to be the heat-affected zone, and this is one of the reasons why prediction of welds using FEA is unreliable. Just a quick note, the content of today's webinar is focused on static sizing and doesn't include other factors such as fatigue. Best practices for looking at weld fatigue assumes that the failure is actually going to take place at the toe, which can be seen just down in the bottom right of the weld there. Okay, so let's look at some of the common or more common types of welds, and here's some of the ones: butt welds, corner joint, T-joint, lap joint, and edge. We'll look at some of these today, but these aren't uncommon types of welds. But one thing to realize about the geometry of a seam weld is that it's not that simple. So why does an FEA model of a weld from a CAD system not match reality? Well, these images will hopefully highlight this. Firstly, we have the CAD model. We've got a uniform, equal leg, perfectly formed weld. But even under the best of conditions, the reality is that welds have significant variability. And here's just a quick illustration. And if you're familiar with welding, you will have seen a range of different weld qualities from this, and possibly either side of it, better and worse. So in addition to geometry variation, we also get a range of other variables that are going to influence the results that we would get from an analysis on a weld with inside of simulation. So if we look at it, we've got things like the geometry of the weld, but also its chemistry, the materials that it's made from, the temperatures associated with it, the preheating and the cooling of the weld are important. The base material, the heat affected zone, things like residual stress after cooling. So all of these things are going to contribute into us not being able to take into account or making it very difficult for us to take into account the geometry of our weld and that zone during our analysis. So it's not, what I'm getting at is it's not realistic to expect that your simulation on welds is going to act anything like what will happen in reality. So can more careful and detailed FEA overcome the variability inherent in the weld to allow better prediction? Well, hopefully you've seen in those last few slides that is very, very difficult. Very difficult indeed. So how do we predict stress in welds? And that's an interesting question. So we've raised a lot of problems. How can we solve them? Well, if you've tried to model welds and then run subsequent simulation, you're likely to have seen this before. This is what's called a singularity. These are unreasonably high stress in areas which the stress is divergent, and the stress location is typically at a sharp transition, as is shown in the image there in the corner. We've already talked about the CAD geometry or the shape not matching the FEA, so I won't go into too much there, but you can quite easily see that It's very hard for us to depict the geometry accurately in those instances. But also remember that if you're looking at stress in the model, where you've actually modeled the weld, it does require that you make an estimate of the size of the weld, and then essentially what you're doing is you're trying to justify why you've chosen that size. In essence, what you're doing is you're trying to justify the weld size that you've chosen based on the stress values that you're getting back. The better solution to doing this would be to design a structure that works the way you want it to work, and then let that model tell you how much weld you need to carry, how much weld that structure needs to carry the load required of it. So just as a quick example, and this is one of a number of examples that we'll use today, here's a part. It's got two sides to it. It's maybe a lifting lug that's mounted to a plate. So what happens if we put two different welds on, slightly different welds on either side of the part? What's going to happen if we analyze the structure? So we've analyzed the structure, and you can see here that what ends up happening is we get diverging stress at a singularity on both sides of the structure. And looking at the welds up close, you can actually see that though the geometry is different, we're still getting the same outcome, and the outcome is not reliable. It's hard for us to trust the results of those. So, this is really proving to us that you're forcing, in essence, though, what we could do is look at modifying the geometry to try and get the geometry to give us a more accurate result, but then how accurate is that geometry in respect to the physical part that we're trying to represent? Another important example of why stresses are likely to be divergent and subsequently incorrect around welds is comparable to classic crack propagation situation, where there's a sharp geometry with no smooth blended corner leading to a single node that's bonded. And stresses in this area are likely to be divergent and incorrect, and potentially polluting the stresses of elements local to them because of their high strain ratio. So it's another thing to keep in consideration. What happens if we assume that everything is bonded and we have a nice smooth weld around the side and it maps to a post-welding grinding operation? Sure, it will converge, but does this match reality? In most cases, people are trying to make their finite element model give them answers that don't match anything that's happening in reality. So what can you do? Well, this is going to be the focus of the rest of our material for today. And what we're going to talk about is finite element methods for modeling seam welds, looking at real-world examples, the pros and the cons. So most engineers want to model the weld. We want to show it on a weld list. We want it to be shown on a drawing. Maybe we want it to be included in our mass properties so we get an accurate mass representation of our design. But is there a time when putting in a CAD-based weld is going to give you better stress results? The answer to that is very rarely and usually under very strict control. So how should you then model welds in finite element analysis? Well, there are lots and lots of ways that people model welds, including some of those listed above. Any one of these is going to give you decent load transfer, which is really what we're looking for, is the transfer of load force between adjacent geometry. But that's about all you can expect. With some of the more preferable ones that you see here are most likely going to be items 3 to 6. The reason for maybe staying away from the likes of number 2 is the fact that in this instance, in using plates and a solid fillet welds, we're actually using mixed mesh. We're using elements which are a two-dimensional planar element with a three-dimensional or solid element. And in doing so, we're adding unnecessary error to the calculation associated with it. Remember, in this instance, and today we're predominantly focused on thin-walled sheet metal structures where the shell elements are most appropriate. We'll look at solid elements at the end of the webinar, but most of the focus is going to be around shell elements. So again, focusing on some of the common methods, some of these are harder than others. In some instances, some of them take much more time to make sure that the meshes line up and thicknesses and nodal connectivity where you want it. They still introduce error, often associated with mixed meshes and contacts, and all of the examples will transfer the load reasonably well. But which one should you use? Well, that really comes down to looking for something that's going to allow you to understand good load transfer, and you want this information, you want to gather this information as quickly as possible. So how do we decide loads statically? Well, firstly, we need to assume that a weld can be sized that carries the load, and design your shell geometry without any additional attention to the weld bead itself, unless that weld bead adds, 1, significant local stiffness, or 2, if it's a dynamic or inertial situation, then that adds significant mass to your design. So they're really the two key considerations for whether you include your weld beads in your analysis. 1, whether it adds stiffness to your design, and 2, whether the mass of your beads is going to affect the dynamic or inertial loads of your design. Most times though, welded structures are many more times the magnitude in size of the weld bead itself, and so leaving it out is not going to make a significant global difference in the global response of your product. So once you've identified that the model behaves well, you can start looking at then the areas of high stress and investigate the loads going through the welds in those specific areas. So the technique that we're going to talk about the most today is what's called throat shear, also known as the treat lines as welds method. And this method is extremely well documented and still one of the most reliable techniques for getting a good understanding of what weld size is necessary in your designs. By using this method, you're not required to make any initial assumptions on weld size, and because you're using forces instead of stresses, our results are going to be less sensitive to geometry and not mesh dependent. Again, these techniques are very well documented. You'll find a range of common references to these, and most likely if you look around your office, you'll find an example of these such tables in engineering reference books that include them. So this example here was taken from Shigley's, which is one of the more common mechanical design reference manuals. I've got a copy of it sitting right in front of me at the moment, and it's common within sort of the education and industry to use a tool like this when helping you size welds. So if you're to run through the hand calculations for this example, you're probably going to run through about 3 pages of calculations, and it's going to take you around 45 minutes to an hour to do that. So for those of you though who are lucky enough to be using Inventor, Autodesk Inventor, you already have access to a tool that can make this process much easier and faster. So the fillet weld calculator that comes inside of Inventor, as can be seen on the screen here, gives you the ability to quickly and easily calculate fillet weld sizes based on a range of geometry and loading criteria. All you do is simply add the information and hit calculate, and basically instantaneously you've got your result. So what would have otherwise taken considerable amounts of time and understanding becomes much more manageable as part of your design process. Now we get a slightly different answer, but in this case it's more conservative, so I'm less concerned than I would be if it was the other way around. This works for more complex calculations as well. So here you can see an example of a plate with combined loading and the subsequent calculations that we've used to understand the minimum throat size of the weld, which comes out to be about 0.177 of an inch. Now my apologies here for the imperial units. I was hoping to convert them before I did today's webinar, but I just simply ran out of time. At the end of the day, the calculations still remain. We're just considering the units as being different as what we might use otherwise here in Australia and New Zealand. So if we take the same example into Inventor's fillet weld calculator, you can see here that we've practically get identical results. So instead of 0.177, we get 0.180. Again, using this calculator takes seconds and potentially avoiding issues with wrong equations, unit conversion, and all kinds of bits and pieces. So it really does simplify that process. What you might notice is that at some point you're going to reach the limits of using these calculators, and there may be loads that are too complex to capture using either the calculation and even potentially using the calculator, sorry, and even then using hand calculations. Though hand calculations are fine for simple geometry, the problem is that most things we design nowadays are much more complex than they've ever been. So it's going to be hard to relate this back to a standard equation, often leading to gross simplification of our designs to fit the equation. So this is where FEA comes into its element. Here we're using a simple example. It's actually a test model. And using it, why would you use a test model? Well, you would use a test model because it's a great way for you to understand what's happening in FEA rather than to try and do it on a much larger, more complex example, such as the design that you're working on at the time. In this example, we have a load combination, including normal, shear, and bending moment loads. You'll notice that the units we specify here are shown as mass per length. Now this is important because it keeps in with the treats Welds as lines method. So, and this is a really good mindset to get into as you're working through these types of problems, is to consider that the weld force is a function of load on length. So before you open up Nastran In-CAD, one of the things you want to do is to consider these 4 tips. Firstly, you want to make sure that we get the force output in the right orientation. And many solvers, including Nastran In-CAD, use or associate force output in relation to the element orientation. So you need to make sure that you're considering the orientation of your element prior to using the force output from them. Make sure you turn on no averaging within the plot options to ensure that you're not getting element averaging of all of the surrounded elements. So you really just want the element force of that specific element, not all of the other ones surrounding it. And when creating an analysis, you also need to ensure that you check the force option under output sets, otherwise the forces won't be considered in the calculations. And another great tip is to use grouping. And using grouping helps you group together a common group or set of elements to help make calculations much easier. So here we are, we've got our simple plate that we've run an analysis on, and you can see here that looking at the load, we're essentially looking at the load transfer across that area. Now note that the no averaging option means that we can actually see the loads on the individual elements rather than taking into account averaging across adjacent elements as well. We can see that for the normal and the shear forces that we're taking the average, and that essentially matches with what we previously defined when we set up. So we said that there were going to be 200 pounds per inch, and both of those are 200 pounds per inch. You will, however, note that there's hot spots at the ends, and if you're, these are, you'll come to expect these in this area if you're accustomed to looking at analysing welds on structures before. So this is not an uncommon thing to see. But why the difference in the bending force, which we had previously stipulated as 400 inch-pounds per inch, and you can see here it's calculated as 375 inch-pounds per inch. Well, that's because the centroid of the element is not at the junction of the corner. So in essence, the 2-inch length of the vertical member isn't completely 2 inches long, because the element is located in the node is, the centroid of the element is located at the middle of the element. You don't get the complete 2-inch length. So how do we solve this? Well, the easiest way to do that would be to add mesh refinement along the edge of that shell element, and then reduce the mesh refinement down to a significantly small value that you thought that was then accurately represented, the bending moment in this case. So using this information on our more complex problem, we can find our normal shear and moment forces, and you can see them here. And then using this information, we can then put this into a commonly available formula, and we can get the weld size, which comes out to be about 0.28 inches, whereas if we compare that against the reference solution is 0.22. So again, why the slight variance? Well, this might be because of rounding errors, or the forces have been summed, the way the forces have been summed. In the world of welds, though, this is a good match and has led to a more conservative solution. So again, not overly concerned in this case. Again, this could be done in minutes versus what could take many more times longer using hand calculations. And note that the weld is divided by 2 as we've got welds on either side of the plate, so it's a double-sided weld. So how does this compare to solids? Here's the same case or same model, but in this instance we've modelled it as a solid, and it's been meshed and solved as a solid. Even the welds included. In this case, the weld size has been depicted based on our previous calculation, rather than us making an assumption. The max legend on the left-hand side has been set to be the tensile length of the weld electrode. So it's the maximum, or the yield tensile, or the strength of the electrode material. It's clear to see that the stresses are dominated by areas where sharp edges are present, like those on the chamfer, suggesting singularities. The stresses are spread out into the face of the weld, so how realistic is this? It's hard to say. Solids, though, provide a very skewed look at the weld because of everything that's going on. Remember, there's also lots of other variabilities that are not taken into account. Here, if we go back to some of our earlier slides talking about temperatures and material compositions, there's a lot of things that we're not taking into account in this instance. So how reliable is it? We'll be approaching it in the same way we have with shells. So what's the best way of using a solid? Well, really we should be approaching using solids in much the same way as we've looked at using shells. And that is to use the solids to give us further information about the loads that are being passed between those two plates there, rather than using the loads to determine the stress on the welds themselves. So here's the example of using a solid mesh, and we've represented this as a section through the model, and this is what's known as plane stress. Taking into account that we're interested in results at the weld throat, see how convergence is actually achieved relatively quickly. And though running and solving this example can be done quickly, consider for a moment that this is a very small section of what might be a very large overall weld. For instance, one from a truck trailer body, and that would take considerably longer and would be much more complex and tedious to solve. Nonetheless, we get an average stress through the throat of about 2005 psi, so circa 2000 psi. Doing a quick sanity check using Inventor, using the Inventor weld calculator, we get an approximate a value of around 2011 psi, so about the same. We're in the same region. And then using the plate model and the force method we talked about earlier, this gives us again very comparable results. We're looking at about 2070 psi, so around the values that we've previously achieved. In each of these cases, we get to the same place. We effectively end up at the same result. But using the plates and force method, we've done three things. We've, one, saved a significant amount of time in modelling. We've, two, saved a lot of calculation time as solving the model. And three, we're still able to achieve a reliable answer at the end of the day. So if we look at the three methods that we've used, and this is a bit of a summary, it's clear that using something like the Inventor weld calculator is great because it gives us an accurate result basically effortlessly with very little time and resources required whatsoever. At the other end, we can use a solid mesh. This is going to take considerably more amount of effort and is very dependent upon a wider range of variables and assumptions. And in this case, it gives us a similar result, but it has taken much more time and complexity to obtain that result. And as we've tried to highlight, using the plate mesh is a great compromise for instances where the geometry loading is too complicated for the weld calculator and gives comparable results but with much less effort and assumptions than using the solid mesh. So, when do you need to consider adding weld elements? So we've said basically, you shouldn't include them for the better part, and use the load transfer between plate elements to then size your weld. So when do you use weld elements? Well, this really does go back to something we spoke about earlier, and you really need to ask yourself the question, will the weld affect the stiffness of my part, or am I concerned about the dynamics of my designs to incorporate it into the calculations? They're really the two parameters that you need to consider. Is it going to affect the overall stiffness of my design? Are the dynamics and the weight of that weld going to impact the dynamics of my design? So in summing up everything, it's often best to use tried and true, and will likely give you a faster result than it would by using a solid mesh to understand your welds. Obviously remember your safety factors, and where possible keep it simple, and as well use your common sense. If we come back to that first picture, hopefully you will have seen that an idealized weld and a photo of a real weld is usually enough to bring people back to earth when they're trying to understand the best way of representing their welds with FEA. So if you're after more information, like I said, Vince's presentation, and this was a very small summary of Vince's much more in-depth presentation. You'll find that on YouTube. Just do a quick search for predicting and validating welds with FEA in Autodesk Nastran In-CAD. I believe it's on the Autodesk Simulation Group's YouTube channel. You can always reach out to your reseller and ask them for some further information about Nastran In-CAD or any of our other simulation tools. If you've got any feedback or questions specific to the content that we've delivered today, my details are there. Feel free to connect with me on LinkedIn or shoot me an email directly and ask me those questions. But otherwise, I will thank you for your time. Let me have a quick look and make sure there are no questions. Nope, nothing specific to today's content. So what I'm going to do is assume that hopefully that's all been digested well and truly. If there's anything you need to follow up on, please do. Just get in touch with me in whatever way that you can. Otherwise, I'll leave you to enjoy your day. It actually was a little bit sunny in Melbourne a little earlier today. Hopefully it stays that way this afternoon and through the weekend. But otherwise, thank you for your time today, and hopefully we'll see you next time. Bye for now.